Thank you very much. So let's continue with the obstacle problem. And so basically, I want to start where we left basically last day, which was that we showed that for the obstacle problem, if we have any singular point, then there exists a quadratic polynomial such that the blow up is exactly, and it is unique. The unique blow up is of this type. Okay, it's a quadratic polynomial that is non-negative and vanishes at the origin. Okay, and so we did this with a monotonicity formula, but basically the point here was that the fact that the blow-up is unique, it allows us to say that the singular set is somehow nice. Okay, and for this, so you have to remember what is the kind of blow-ups. So this is a quadratic polynomial. So in particular, the zero level set of this, so and this has Laplacian 1, so it cannot be like 0. So the zero set of this is a linear subspace of a Rn of dimension, well, either from 0 to n-1, right? So just keep this in mind, okay? And then we know this, and then we saw this was proved thanks to a monotonicity formula. And then remember, this is what we are saying, that the rescaled versions of U converge to this quadratic polynomial P that depends on the point. And then we have some continuous dependence of blow-ups. Okay, this was this result that was saying that if you consider the unique blow-up at every point, then this blow-up is continuous. The dependence on this polynomial on the point is continuous. Okay, and moreover, we have this kind of expansions for U and for the gradient of U with a modulus of continuity. Okay, so here, notice that x squared is the size of U and P. Okay, so having a modulus of continuity is like the least information, the minimum information we can have, so that this is telling us exactly this, that the rescaled versions converge to this blow-up. Okay, and then we saw that using these modulus of continuity, one can show that the singular set is contained in an n-1 dimensional C1 manifold. Okay, and then the n-1 comes from the fact that, so this is the dimension, the largest dimension of the zero level set of these polynomials. Okay, so in 2D, here we are saying, if we are in 2D, we are saying that the singular set is contained in a C1 curve. Okay, so we have in 2D, for example, we have a picture like this, and then this theorem is saying we have some regular points in which everything is infinity, and then we might have some singular points that could look like this. And basically, this is our cusp, and then this would be, here you could have, for example, any subset of a C1 curve. Okay, but by this theorem, this is the worst that can happen. You cannot have really a singular set that is spread out everywhere and so on. Okay, so it is really n-1 dimensional and contained in a C1 manifold. Okay, and then so this picture is something that can really happen. So you can build examples of this happening with a infinity obstacle, basically. And then so this subset could be even, I don't know, a Cantor subset of this one-dimensional curve. Okay, but this is kind of, well, this happens, and this theorem tells you that this has the right dimension and that it is C1 at least. Okay, and then so to prove this, the idea was that, well, U is well approximated by this polynomial, and therefore say that this polynomial, so in worst case, in 2D, basically, the worst case would be, say, you either have like x1 squared and x2 squared, and then the zero level set of this polynomial is just a point, or you have simply x2 squared over 2, right? And then if you have this, then the zero level set of this polynomial is a line. Okay, so you have to imagine that we are comparing the zero level set of U with the zero level set of P, in a sense. Okay, and then because of this expansion, this is telling us that if the zero level set of P is a line like this, then the zero level set of U should be trapped between two curves that are really tangential to this line, which is the zero level set of P. Okay, and this follows really from this expansion, because if P is positive here, then U is positive here by this expansion. If P is positive here, then U is positive here by this expansion. And because the expansion is better and better as we approach the origin, that's why this curve is closer and closer to the point as we approach the origin. And then it turns out you get something that is really like C1 here. Okay, and then because you can do this at every point, so the idea is that the blow up gives you what is the tangent plane, because this is really telling you that at this point you have a tangent plane. Okay, and is the tangent plane of the blow up. So is the line, the zero line of the blow up. This is your tangent plane. Okay, and then the idea is that the blow up gives us the tangent plane. Okay, so at every point you have kind of a tangent plane for the singular set somehow. Okay, and then the continuity of blow ups implies that at every point you have this tangent plane, and then the tangent plane is continuous because the polynomials are continuous. Okay, and then thanks to Whitney extension theorem, you can prove that this kind of information implies that the whole singular set is contained in a C1 manifold of dimension n-1, and the n-1 comes from, well, what is the dimension of the zero set of the polynomials? Okay, what is the largest dimension of the zero set of the polynomials? Okay, so this is basically the idea of how to prove, and this is the classical theory in a sense, about how to prove this theorem, which is due to Caffarelli. Okay, and now in this last lecture, I want to show some more recent results about the singular set here for the obstacle problem. Okay, so this is the picture to have in mind, and this is the kind of singular set. Then, of course, in higher dimensions, more things could happen, because then if you are in R3, for example, then the zero set, the singular set could be contained on any, a priori, any C1 surface. Okay, so it could be, the singular set could be any subset of C1 surface. Okay, and this could be, I mean, this looks bad because you could have very weird examples, but we want to see if we can say more and more. Okay, so basically, also notice before starting to get finer results, I mean, some first thing to notice is that you can have, for example, in R3, different behaviors for the singular set. Okay, so one thing that can happen is a cusp like this, and here, when you do the blow up, the zero level set of the blow up becomes a line in R3, right? So this is, and then you expect this to be contained on a line in R3. While, so this is in the polynomial, in this case, could have like x1 squared and x2 squared, say, because then it's positive in two variables in a sense, right? So it's zero only on a line. While here in this other example, you could have a cusp, a kind of cusp in R3, but in which the singular set and the blow up, the zero set of the blow up, you expect it to be two-dimensional, something like that. And then these are all singular points. And then here you could have any subset of this surface, say. Okay, so these two behaviors are actually different. Okay, and we can separate them, we can distinguish between them by looking at the blow up. Okay, so can we have a theorem about this? Can we have a theorem that distinguishes between this kind of behavior and this kind of behavior? And the answer is yes. Okay, and then, well, the last kind of points, of singular points, would be points like this, in which they are isolated points, really. And then the blow up would be, for example, in R3, something like x1 squared plus x2 squared plus x3 squared, say, divided by 6. And then at these points, really, the points, you expect them to be isolated. You can, if you have kind of singular points where the blow up is really positive in all directions, then you expect isolated points. And so the blow up in all these cases, as we saw, is a quadratic polynomial. Okay, but in 3D, so the distinction between these three kind of behaviors is the dimension of this zero level set. Okay, so it can be either a plane or a line or a point. This is the zero-level set of a quadratic polynomial, right? And then according to this, we can have the following definition, which is that for any m less or equal than n minus 1, we can have, so we split basically the singular set into some pieces that I call sigma m. Okay, so, and then m is the dimension of the zero set of the blow up at that point. Okay, so I take as a sigma m the singular points such that the dimension of the zero set of the blow up is m. Okay, so this would be sigma 0 because here these are zero dimensional zero set of the polynomial. This is sigma 1, which is the one that I expect to be like one dimensional, and this is sigma 2, where I expect things to be two dimensional. Okay, and then basically because of this expansion, okay, you apply the same reasoning that we had before to show that, I mean, to have the idea of why the singular set is contained in a C1 manifold, and then the same argument, the exact same argument, it tells you that the manifold, so this is true, but moreover, the manifold is of the right dimension in a sense. Okay, so we can have a general theorem for sigma m for every m less or equal than n minus 1. Okay, and this is the result that I wanted to state now. Basically, if we have this is sigma m, then with the same proof we get that the set sigma m is contained in an m-dimensional C1 manifold. Okay, and then for m equals 0, these points are isolated. For m equal 1, it tells you that these points are contained in a C1 curve, and for m equal 2, it tells you that these points are contained in a C1 surface in R3. Okay, and this is true in every dimension. Okay, then so if you take the singular set all together, it is all contained in a C1 surface. Okay, but you can say a bit better and then split the singular set into pieces and say, okay, this is a C1 surface. This part is contained in a C1 surface. This part is contained in a C1 curve. This part consists of isolated points. Okay, so this is the best basically that was known until some years ago. Okay, and this is still due to Caffarelli in the same paper in '98. Okay, so now the question that we have is this the best we can say about the singular set? Okay, so can we say something more? And the answer is yes. But for example, the right questions to ask maybe are, well, can we improve the convergence of blowups to something like this, right? So because we saw that we have a modulus of continuity for the blowup, which is like the least you can say is having a modulus of continuity like small o of x squared, right? Because this is what gives us all this information and the fact that, so the C1 manifold, it was really crucial to have a modulus of continuity, but maybe we can improve the modulus of continuity to something more explicit or something better, like say x to the 2 plus alpha. Okay, so having a Helder modulus of continuity. So can we have this? So this would have a better expansion in a sense for blowups at singular points. Okay, or very related to this is the singular set contained in a better manifold, in a C1 alpha manifold, for example. Okay, so can we improve either the expansion or this this regularity of the manifold in which the singular set is contained? Okay, so this is also a very natural question. So to what extent you can improve this regularity of the singular set somehow? Okay, and then the question, well, why not even infinity? Okay, because all the examples we have are really smooth in a sense. So you can get very ugly things like in the examples before that I said any subset of a curve, but the curve, the only way we can construct it is really infinity. Okay, so one might wonder if this is true or not. Okay, and then another question that was raised actually many decades ago is how often do singular points appear? So in all these examples, so these things can happen. So these kind of examples can actually happen, but to construct one of these examples, you need to be very careful. So it's not something that happens for every solution. Okay, so you basically need to work quite a bit in order to construct solutions with non-trivial or non-small, say, singular sets like this or like this. I mean, this is difficult to construct, to have something like this. Okay, and so the question is, well, maybe the singular set is in general n-1 dimensional, but say this does not happen often. I mean, maybe you can prove that this is very rare, very unlikely to happen. Okay, so in general, we wonder, and this was actually a question raised in the 70s, how often do singular points appear? Okay, and this is something we will talk about now. Okay, so in a sense, the question, in other words, is, does a generic solution have singularities? Okay, so if you take a random solution, a generic solution, does it have singularities or not? Or at least, can you prove that the singular set is smaller and not so large? Okay, and these are the questions that I want to discuss today. Also, I mean, other questions would be like, can you have infinitely many cusps and so on? I mean, you can ask many questions about the singular set, because basically the only thing that was known was this, which is a lot, but still raises many questions. Okay, so these are the questions that I want to discuss here, and as we will see, all these three questions are very connected. Okay, so these two questions you can maybe deduce that they are connected, because, for example, once we had this expansion with a modulus of continuity, we got C1 manifold. So it is very natural that if we improve the modulus of continuity to 2 plus alpha here, then you can improve the manifold to be C1 alpha. Okay, so this connection is natural. Okay, and then we will see what happens, or if we can improve this to something better. And then we will see also that it turns out that with the proof of the result of a result that I will present now about the generic solutions and generic singularities, it is actually very related to this also. So this question turns out to be connected to this one. Okay, so what I want to discuss is the following conjecture, which is due to Sheffer in '74. So this conjecture was raised by Sheffer after he constructed several counterexamples, well, several examples, say, of singular points. And then this was even before there was a theorem about regular points. So this was before the papers of Caffarelli. Okay, so this was very early, and he already asked this. So he said that he conjectured that generically, so for a generic solution, free boundaries in the obstacle problem have no singular points at all. Okay, so this is, I would say, at that time especially, was very, I don't know, a bold conjecture, because it was really, I mean, well, he didn't say what generically means. So he really says that because the singular points that he was constructing were kind of difficult to construct, that he believed that generically, in some sense, free boundaries should have no singular points. Okay, so for a random solution, or for generic solutions, in some sense, you should see no singular points. Okay, and as we will see, so this question is very delicate, and we will see some new results in this direction that we established last year. Okay, so the first result in this direction was in 2003, so much later, much after Sheffer raised the question, and was in 2D. Okay, so basically Monod proved in 2003 that the conjecture holds in 2D. Okay, and then the proof of Monod uses, so not only his monotonicity formula, but also it's very 2D, basically. I mean, it really doesn't work in higher dimensions, and uses the coarea formula. I mean, it's very nice and clean. So I think it's a very nice proof and very nice result. And then more recently, we improved this to the following. So we published this last year, and we proved that generically, and I will explain in what sense I mean generically. So, but take a random solution, say take a generic solution, then the singular set satisfies that it has, well, dimension at most n-4, and the n-4 Hausdorff measure is 0. Okay, so this is, so remember that in general, the singular set could be n-1 dimensional. What we are proving is that for a generic solution, so for a general solution, if you don't have very bad luck, in a sense, for a generic solution, the singular set is its n-4 Hausdorff measure is 0. Okay, so in particular, Sheffer conjecture holds up to dimension 4. Okay, so this is telling us, well, so this is solving Sheffer's conjecture in dimensions 3 and 4. Plus, it's giving us a result in all dimensions that is really saying that generically the singular set is very small. Okay, so this is very nice because remember in the Bernoulli problem, we had that for all solutions, the singular set is very small, right? And then the point was to find the right dimension, which is still open. But in the obstacle problem, we saw that the singular set can be in general, so it can be n-1 dimensional. Okay, but this is bad because then the singular set could be as big as the regular set. And now this result is telling us, well, this does not happen generically. So generically, even though sometimes the singular set is n-1 dimensional, which is really bad, generically this does not happen and the singular set is very small. Okay, so in a sense, for the obstacle problem, in order to have a result like the one for minimal surfaces or the one for the Bernoulli problem, you need to consider like generic solutions. Okay, and then you get that the singular set is small. So let me say, let me give a bit an idea of the proof of this result. Okay, so the proof of this, I mean, the published version is 112 pages. So of course, it's impossible for me to give really even a general idea of all parts of the proof. But I will say what are the ideas of some parts of the proof that are easier to follow, I think, and because they are less technical. Okay, so the general strategy, I think it's easy to follow, and then there are many details and things that are more tricky. So basically, the general strategy is that we consider a monotone family of solutions, U with a parameter T. Okay, so, and it's important that they are monotone. So you can think about having a boundary data and you just fix the boundary data, any boundary data you want, as long as it's monotone. Okay, increasing, not even strictly increasing everywhere. I mean, just a monotone family of solutions that is not constant. Say. Okay, so you consider any family of solutions like this that is monotone, and then we denote sigma t to be the singular set. Okay, so ut is the solution corresponding to the parameter t, sigma t is the singular set corresponding to the solution for this t. Okay, and then this is the free boundary. And now let's say, because this is something we prove in the paper, okay, but like for today, let's say we can prove something like this. Okay, so let's say that we have a singular point in sigma, so x0 at sigma t0. Okay, so for a certain point, we have this kind of expansion. Okay, and then let's say that I have this expansion with a certain polynomial here and for a certain lambda here. Okay, as we will see, what we prove is that depending on the point, we can prove this with some polynomial and with sometimes larger, sometimes smaller lambda. Okay, but let's say we have this. So just for the sake of, I mean, assumption and see what we can deduce from this, let's say we have this. Okay, and then if we can prove this, okay, which is like a better expansion at a singular point, okay, and then for some lambda bigger or equal than 2, because we already know it for 2. So let's say we have this for something better than 2, and then a polynomial such that the Laplacian is constant equal to 1. Okay, so this is true, for example, for lambda equal 2, this is true at every point, and then this polynomial is the blow-up. Now I'm wondering, say, if we have this for lambda equal 3 or 4 or 5, and then maybe we have to change the polynomial and to modify it. Okay. But then let's say we have this and see what we can deduce. So then if we have this, then because the solution is non-negative, then this expansion implies already that the polynomial is bigger than minus c times x to the lambda. Okay, so this follows from the expansion and the fact that u is non-negative. Okay, but then this means that in BR, so for every r small, in BR, this polynomial, if we add constant times r to the lambda, will be positive in BR. Okay, so and then this means that the function u, the solution u, is very close to the polynomial, and these solutions are increasing in t. So this means this really suggests that we will have that if I add some boundary data in a sense. So if I add some t here, which you can think about the t to be the parameter that increases the boundary data. So if I increase the boundary data by an amount delta, then the polynomial should become this in a sense. So u should be close to this function, which is positive. Okay, so this is the rough idea, and I'm not saying what is the relation between delta and lambda and so on, but this should be the right idea, that because I have an expansion like this, then I should prove that u, when I add some boundary data, instead of being close to this polynomial, should be close to this one, which is positive everywhere. Okay, and then if this is true, if I can do something like this, then this would mean that there is no contact set in BR. So in particular, there are no singular points. Okay, so and then what we do is to, well, actually prove this, but this requires a series of delicate Berger arguments, and we prove actually that you lose an exponent in a sense. So you prove that if you have an expansion like this, okay, so if we have an expansion like this, then when we add to the boundary data, we add a delta that is comparable to r to the lambda minus 1, then the function becomes positive in BR. So at points where we have an expansion up to order lambda, we get this, that when we increase a bit, the boundary data by then all singular points disappear in a small ball. Okay, and then how much do we have to increase the boundary data? Well, this is very small as long as this is very small, and the smaller this is, so the larger the lambda, the better this is giving us. Okay, and then so this will depend on the type of point. So we might have different type of points in which we have different lambdas. Okay, and this is actually something that happens. And then when this happens, we have this, that the singular set in a slightly bigger t intersection with a ball BR is empty. Okay, so this is, let's say we believe that one can show this for some lambda, and then with these Berger arguments and so on, you can prove this. Let's see the idea of why this is giving us some information. So what is this information giving us? Okay, this is what I want to just make a picture and discuss a bit. And this is the kind of GMT lemma that we prove, that this information is enough to deduce something for generic solutions. Okay, so basically, remember that we assumed we had this, and then we deduced that we have this. Okay, and then the lemma that we need is something like that. So it's a general lemma for sets. Okay, so if we have a family of sets in a Rn, okay, so you imagine this is space, this is the Rn, say, and this is the parameter t. So for every fixed t, we have a set, okay? And then x0, for example, belongs to this set with the parameter t0. x1 belongs to this set with the parameter t1. Okay, so for every t, we have a set. Okay, this is all I'm saying. And then let's say so that we have this property for the sets, that the set, so if x0 belongs to the set for the t0, then this set adding constant times r to the kappa intersection with Vr is empty. So this is exactly, I'm just writing the information we have. Okay, and this is the picture. So the picture is telling us that, say that kappa is large, so here kappa is lambda minus 1. We have that this whole region in the picture is empty. So there is no singular set here. Okay, this is this information. That if x0 is in the singular set, then above all this curve, in all this region, there cannot be any singular points. So I'm just translating this information into an assumption here for sets, okay, with a picture. Okay, so this is the key information to have in mind. For every x0, if this is in the singular set, there are no singular points here. Okay, and the better the lambda, the better this kappa, because it's lambda minus 1. Okay, and then assume also that the whole set E has a certain size. So what do I mean by the certain size? Well, let's say that the union, so the kind of the projection here of all the set, all the singular set, you take the union for all t's, and let's say that the union for all t's of this set is at most beta. Let's say, let's give it a name to the dimension of this projection, basically. So you imagine all the points that are in the singular set for some t, you take all of them and project them here. And this has a certain size, which is dimension beta. And then this lemma that we prove says that for almost every t, which means like generically, for almost every t, the dimension of this set is beta minus kappa, where kappa was this one. Okay, so it's lambda minus 1. So, of course, the smaller the beta, so the smaller the set is, in the sense of the projection, the smaller the set is, the smaller generically you get the dimension for E. Okay, but also the nice thing is that the better you have this, so the larger the kappa here, so the better the expansion, then the smaller it is the singular set generically. Okay, so now this lemma is telling you, yeah, so what you want to do, if you want to prove that the singular set is generically for almost every t, it is small, well, you have to improve this lambda as much as you can. Okay, so this is what the lemma tells us. Okay, so yeah, this is what we have, and then the better the expansion here, the smaller it is. So the smaller the singular set is for almost every t. Okay, so imagine that you had an expansion up to order 5 or 6, right? Then say that beta is n, is the full space, then you already get n minus 5. Okay, so this is really, well, sorry, n minus, if you had the expansion up to order 5, then you get something like kappa is lambda minus 1, so you get a 4, so you get n minus 4. Okay, so this looks like if you can prove an expansion up to order 5 everywhere, you get already n minus 4. If you get better than 5, then even better, right? So this is what we try, right? And this is what you try to get. And then, so the goal we have is for any singular point, make lambda as large as possible here. Okay, as we will see, it turns out that you cannot do lambda as large as you want at all singular points, but you have to split it into pieces. Okay, so and then given lambda, estimate the dimension of the set of bad points where the expansion stops at lambda. So basically, what we will see, what do I mean by stops? So what we will see is that you take a singular point, x0, and then you can try to improve this expansion more and more and more. But then depending on the point, you can continue doing this and get improving it. But at some points, there's some bad points in a sense, this expansion really stops. Okay, and then it is false to have an expansion with an exponent bigger than 2 or bigger than 3 or bigger than 3.5. Okay, so depending on the point, and this really happens, the expansion sometimes stops at order 2, sometimes stops at order 3, sometimes stops at order 3.5. Okay, and then this really happens, and then sometimes you can continue. And then the point here is that then, so let's say that the expansion stops at order 2. Well, then I want to prove that in this case, because I cannot improve the kappa, I have to improve the beta. So the points at which the expansion stops at order 2, I need to improve the beta, which means to prove that this subset of points where the expansion stops at order 2 is very small. So the projection is very small. Okay, so my goal, in a sense, is to say, well, either I have a very large, a very high expansion, or the set of bad points where I do not have the expansion is very small. And this is our goal. Okay, and this is the core of the paper, in a sense. Okay, and then how do we prove the expansions? Okay, so basically, well, we start. We already know this happens for lambda equal 2 with even with a modulus of continuity, and this polynomial being P2, right? So the idea is to consider second blowups. You take this new function u minus P2, which you know this holds with lambda equal 2, u minus P2, and then you rescale and divide by its size by a norm in BR, say, so that this has norm 1. Okay, and then you consider these functions and then try to prove that this converges to something. And then let's try to see, because with first blowups is how we could prove that we had an expansion in a sense up to order 2 with a modulus of continuity. So why not to continue a better expansion? This is what you would do for a function, right? If you have a function and you want to find like what is the second derivative, well, you subtract the first term in the expansion and then kind of rescale. But here is much more tricky because you have to subtract this blow up. Now, u minus P2 does not solve exactly an equation, but almost, and you divide by the size of this, which you don't know what is the size. Okay, and now u minus P2 is harmonic wherever u is positive, and it's not negative where P2 is 0, and it's a super solution. Sorry, a subsolution everywhere. No, super solution. Yeah, sorry. And then you let r going to 0, and you find that formally, at least, this function will converge to something. Okay, to a function q. Okay, so proving convergence is not easy because you need some compactness and so on. But let's say that at least formally, this you can pass I mean, it will have a limit. And then what is the limiting equation for Q? Well, at least formally, notice that the set where U is positive in the limit becomes the set where, well, everything except for P2 positive. Sorry, except for P2 equals 0. So the set where U is positive converges to the set where P2 is positive, okay, which is this one. And then this condition simply stays. So u minus P2 is not negative wherever P2 is 0. So I get that the function is harmonic everywhere except on this linear subspace, because I know this is a linear subspace. Then Q is not negative on this linear subspace, and Q is a super solution everywhere in a red. Okay, so these are the informations I have for this limiting function Q. Okay, at least formally. This is not a proof, and this is really not something you can prove in all cases, but let's say this is at least formally what we get. Okay, but what is this? Well, this is the thin obstacle problem. Okay, so in other words, when P2 equals 0 is a hyperplane. Okay, so when this is so it depends on the dimension, and this is why I say here in sigma n minus 1. But when this is a hyperplane, then Q, this is the thin obstacle problem. So this function Q, this limiting function Q, solves the thin obstacle problem. Okay, so I take second blowups and I get solutions to the thin obstacle problem. Okay, in sigma n minus 1. And now, what if this set is smaller? The P2 equals 0 is not a hyperplane, but is something of less dimension. Well, then if you are harmonic here, you basically prove that you are harmonic everywhere. So this does not matter, and this does not matter, and this does not matter. You really get a harmonic function everywhere. Okay, so, but let's say we stay in sigma n minus 1, which is the worst set, okay, because it's the largest. So in the largest set, which is sigma n minus 1, Q solves the thin obstacle problem. And now we have two cases. Either it's really a solution to the thin obstacle problem, in a sense that you see not a polynomial, okay? And then we have to treat this case separately. Or maybe Q is just harmonic, okay? So maybe you are a solution really of Laplacian equals 0 everywhere, and then it's a harmonic polynomial. Well, then if we get a harmonic polynomial, we can do the same again. Put the polynomial back here. So because this will give us basically that u minus P2 minus this new polynomial Q, we would have an expansion up to order 3. Maybe without the modulus of continuity, but at least let's say we have an expansion up to order 3. Okay, and then the idea is that you can try to continue doing blowups. Okay, so you subtract the P3, then you consider u minus P2 minus P3, you rescale, you divide by its norm, and see what happens. Okay, and then again, you get a solution to the thin obstacle problem. And again, you might have you might have some luck and get that the Q is a harmonic polynomial again, and so on. Okay, and then while you get a harmonic polynomials, you can continue improving the expansion. Okay, and if you get a solution to the thin obstacle, a non-trivial solution to the thin obstacle problem, then, well, you have to stop because these will not be polynomials anymore. It will be really non-trivial solution to the thin obstacle problem, and then all the arguments before do not work. Okay, and then let me say also that to keep doing these blowups, so for P2, it is kind of reasonable, but then once you want to subtract P3, this becomes more delicate. And then if you try to do order 4, each time is more delicate. And then in our paper, basically we can get up to order 5 or 5 minus epsilon, and this is the best we can get. And the argument is different in each case. So we need really to work a bit, in several steps, and the ideas are different depending on if the harmonic polynomial is even degree or odd degree, etc. Okay, so there are many technicalities there. Okay, but let's say we can continue doing this, and then if Q is not harmonic, then the expansion stops, and we need to understand the set where this happens. Okay, so when the expansion stops, then we basically need to prove that the set in which you get a solution, a non-trivial solution to the thin obstacle problem, this set is small. Okay, so we want to prove that the set where the expansion stops, it is really small. Okay, and this is something we do, and then we need to separate in the singular set into several pieces, and then actually we are kind of lucky because there are some points at which the expansion stops at order 2. Well, then at these ones, they are only on the lower dimensional, on the m less strictly than n minus 1. And then for these ones, we can have some better barriers, and we construct somehow better arguments that do not involve this expansion, but only barriers. And then we prove that this set is very small. And then when you stop at order 3, then you need different kinds of barriers and different kinds of arguments to show that this set is small. And in all cases, basically, everything is based on barriers and dimension reduction. Okay, so dimension reduction, so this is a typical kind of argument in GMT for that comes from minimal surfaces, and you need a monotonicity formula. Okay, and this is because I didn't say it here, and this was already contained in a previous paper of Figali and Serra. So this function u minus P2 satisfies, so it has an Algren monotonicity formula, an Algren frequency formula. And this is why you can do this second blow up. Okay, basically because you have an Algren frequency formula. So these blow-ups will be homogeneous, so we can classify them a bit better, and then we can do dimension reduction and prove that these sets, these bad sets, are small. Okay. And basically, I think this is everything I wanted to talk about. We have some last slide with some open questions. Let me also mention that there is also a more recent paper that is it's Federico Franceschini and Victoria Ros-Oton, who were two PhD. Well, Federico is a PhD student at ETH, and Victoria was a PhD student of mine at the University of Zurich. And they proved that you can really continue with this expansion. So as I said, we stopped at order 5 because this is really the best we needed for the Sheffer conjecture. Okay, so continuing after order 5 does not improve Sheffer conjecture in higher dimensions, but it's really nice because it gives you an extra information, which is that they found they improved our arguments, and then they could prove an expansion up to order infinity. Okay, so they really proved a really nice result about the singular set in the obstacle problem, which is you have most of it, okay, not all of it because we know it's false, but most of it is contained in a infinity manifold. Okay, and this is the best you can say. So you have the singular set is contained in a infinity manifold up to a smaller set of dimension n-2. And this is for every solution, not generic, not anything. I mean, for every solution, you have a infinite expansion at most points, and then the ones where you don't are of codimension 1. Okay, so let me finish with some open questions. Well, the first obvious question is, well, can you prove Sheffer's conjecture in higher dimensions? Because we proved that the singular set is very small in all dimensions, and that Sheffer's conjecture holds up to dimension 4. But, well, it's still open if one can prove Sheffer's conjecture in dimensions n bigger or equal than 5. So basically, the question would be, is it even true? So what is the best one can do with this? So what is the best one can prove in terms of generic regularity of free boundaries? Okay, so notice also that our theorem, when we say generic, is something very, very general. So it's really, you take any monotone family of functions, and then for almost every parameter t, then the singular set is small. Okay, so maybe, and then these arguments seem really sharp. So it's not that you see how to improve it. So if you want is to improve Sheffer conjecture in dimension 5, for example, it seems like one would really need a much better understanding of what is happening with the points without the expansion. Okay, so with our expansions, the best we could say was up to dimension 4. And if we are to prove something in dimensions 5 or higher, I believe this should be a completely different argument. Okay, so maybe one has even to choose some specific perturbations, and then the term generic should be understood in a bit less general way, because in our theorem, it is really general in the sense that you take any family of solutions, and then you get the regularity for almost every parameter. Okay, so, but this is a really nice and difficult open question, which is what happens with Sheffer conjecture in dimension 5. So it's not even clear if it's true or not, or in which sense it is true or not. It might be that in our sense it is false, in our sense of generic, but you can take some specific perturbations and then it is true in all dimensions. I don't know. Okay, and then another nice problem that in which we had some recent progress due to Simone Berle, Henrik Schagolian, and Georg Weiss was the following. So can we have a complete classification of global non-homogeneous solution to the obstacle problem in Rn? Okay, so this is still open in R3, for example. So you take R3, and so in 2 dimensions this is known, but because it's related to, I mean, you can use complex analysis methods. But in R3, this is still completely open, which is, can you prove a complete classification of global non-homogeneous solutions? Okay, and then there is this nice result that is very recent, that is for dimensions n bigger or equal than 6, if the global solution is really like 6-dimensional in the sense that it's thin in some dimensions, then they completely classified global solutions. Okay, but it's still open what happens in dimensions 3, 4, 5. Okay, and then another very nice and difficult question is, well, can one classify blow-ups completely in the thin obstacle problem? Okay, so this is a question that is very interesting in itself for the thin obstacle problem, but it has also some, it would have some applications also for the obstacle problem, for the classical obstacle problem that we were discussing here. Okay, because the second blow-ups are solutions to the thin obstacle problem. So if you understand better solutions to the thin obstacle problem, you understand better also solutions to the classical obstacle problem. Okay, but this is also really, this seems very challenging. Then for the Bernoulli problem, the most natural question and famous, I would say, is, well, can one classify blow-ups in the Bernoulli problem in dimensions 5 or 6? Okay, so this is also a really nice question that still requires some new ideas. And then there are many questions in non-local versions of these problems. So you can have the obstacle problem for the fractional Laplacian or for non-local operators in general, and then also like the Bernoulli problem, which is sometimes called the thin one-phase problem, because it's a thin version basically of the Bernoulli problem. These are all non-local versions of the obstacle problem or the one-phase problem, in which many questions are still open. Okay, and then for example, in the Bernoulli problem, we don't know how to, in the non-local version, we don't know how to classify blow-ups even in R3. Okay, and then for the obstacle problem, for the non-local version of the obstacle problem, we don't know much about singular points, except for the case of the fractional Laplacian. Okay, or if we are even in the fractional Laplacian for the parabolic version, then we don't know anything about singular points as well. Okay, so there are many open questions in non-local versions of these problems. And yeah, there are many also interesting problems, like for example, this is the Alt-Phillips functional. And then this, so remember, when gamma is 0, this is the Bernoulli problem. This is basically the functional corresponding to the Bernoulli problem. When gamma is 1, this is the energy functional for the obstacle problem. And then what a very natural question is, well, what if I take a parameter gamma here? This is the Alt-Phillips, and this was studied already in the 80s. What if I take this problem here, this energy functional, and study solutions? And then I think for this problem, for example, there are open questions in terms of the classification of blow-ups. I think Tomas Sant Perella has been working on this recently. Also, an open question here is, well, I think it's known that flat free boundaries are C1 alpha, but it is not known if C1 alpha free boundaries are C infinity. Okay, and this is very delicate here. So there are many open questions in this context, and so I will stop here, and I'll be happy to discuss if you have any questions or comments about this.